Great. All right, thanks everyone for being here. And today I will kick off this session by giving an introduction to how we can study neutron star matter with gravitational wave with neutron star mergers. There are two more ways to use gravitational waves to study neutron stars. The first is by neutron stars in isolation, and the second is, of course, by protoneutron stars during supernova explosions. For the second, we'll have another talk later, but I will be talking about mergers in this talk, neutron star mergers. Okay, so we're talking about neutron stars here, observations of neutron stars. So this is macroscopic observations of big compact objects. So on the right, you have the mass and the radius of those neutron stars. So we're talking about solar mass, order masses, and radii of a few kilometers. And the way the connection goes here with dense matter is, of course, that all the models for the mass and the radius of the neutron star you see in different colors are in a one-to-one correspondent with microscopic models for the dense matter properties that are on the left-hand side. So each of these equation of state lines on the left-hand side describing the pressure and the density side, the neutron stars, correspond to something on the right-hand side, the macroscopic properties of neutron stars that we can study either with gravitational waves or with electromagnetic observations. The different models predict quite a bit of variation in the radii of neutron stars. You see that you have radii possible from 10 kilometers up to 15, 16 kilometers. Not all of these are viable today, but there are models that predict that. And this sort of 50% variation in what the radii of neutron star possibly are is quite big for us for astronomical observations. It does have an observable imprint on what we see or on our observations. So we can play the game backwards using our observations to measure neutron star macroscopic properties. For neutron star mergers, the story is basically the following. So this is a numerical simulation of two neutron stars. They are in a binary, they're orbiting around each other like anything in a binary does under gravity. On the bottom, you see the gravitational wave signal they emit, and at first they're far apart, just orbiting around each other, but right about now, they get close enough together that the properties of neutron star matter affect the evolution of the system. I'm gonna play the late stages again, but you can kind of see that the neutron stars start as nice spherically symmetric, but eventually by now they're tidally distorted before the merge. And during the merger, of course, they form another extremely dense and extremely perturbed object that keeps emitting radiation. So this is the kind of system that we're after, and this is the kind of signal that we're mostly after. A neutron star coalescence with gravitational waves looks something like that. So this is a plot of the amplitude as a function of frequency. We do everything in the frequency domain. And the blue and gray lines here you see are the sensitivities of our detectors on this plot. So the further down those curves are, the best it is for us because the more sensitive our detectors are. The blue was sensitivity a few years ago when the first binary neutron star detection happened, and the gray is the desired sensitivity a few years from now, the design sensitivity of our detectors. And the different lines that go down in frequency mostly with different colors are example gravitational wave signals from binary neutron star mergers with different equations of state. So neutron stars with different dense matter properties. So early on, the vast majority of the signal we're seeing is a so-called Inspiral, where you see that the different colors give sort of the same signal, which means that the equation of state does not affect the signal at this stage. This is where the neutron stars are sufficiently far apart that the details of their composition doesn't affect the signal. They're effectively acting like black holes with no internal structure. This is the vast majority of the signal we're observing. This lasts for 2 minutes when we observe the first signal. Even more, a design sensitivity could last up to 10 minutes, 10, 15 minutes. But this signal is not so interesting for equation of state studies, but it's still useful because it tells you things like the neutron star masses or the neutron star spins. Eventually, when the neutron stars get close enough together, this is what we call the late Inspiral, where the tidal interactions start, and you start seeing that the signals, different colors are different. You can tell apart the different colors. So the equation of state does predict a different signal depending on exactly what the neutron star properties are. Eventually, the neutron stars will, of course, collide. They will form a very dense, distorted object that will keep emitting signal. This is called the post-merger, which has unfortunately not been observed today, but it is a great opportunity for the future because as the detectors are getting better, we believe we can see that as well. And it also carries information about the equation of state. Okay, so let's talk a little bit about the Inspiral first, which is by far the most promising signal. As you can see, it is the one that is still above the detector sensitivity, the detector noise in blue. So it's the signal we have seen today. So I'm going to show you two more simulations to describe how exactly the equation of state affects the evolution of two neutron stars. So these are simulations of neutron stars that have the same properties, same masses, with the same location, and let go. The only difference is the equation of state. And you can see that on the left and on the right, the neutron stars on the left are bigger than the neutron stars on the right. So the radius is larger on the left than the radius on the right. All right, and if I press go, can you still hear me?
Yes, we can, and we can see the video as well.
Oh, okay. I'm sorry. I just lost like the panel image, and I was worried I lost connection or something. Okay, so let's play this again and press go the simulations. And you can clearly see the difference already. The neutron stars on the left are going faster than the neutron stars on the right. The system is evolving faster, and it's already merging, while the ones on the right are still orbiting around each other. So the general rule of thumb is that the bigger the neutron stars, the more tidally deformed they are, so the larger this whole process goes. Of course, the ones on the right will eventually merge, and that's also happening here. It just takes longer. Yeah?
Sorry, I'm sorry. It turns out there was a question by Mike Famiano. He asks, back in slide 4, what causes the spikes in sensitivity?
Oh, you mean the blue? Yes. So this is actually
Exactly.
spikes in anti-sensitivity. So we're not sensitive in those frequencies because remember we need this to be low to be sensitive. So these are various resonances in the system, in the detectors. So you can have things like, so our detectors are basically test masks are suspended from pendula, and those pendula have eigenmodes, they have resonances, and in these resonances we're not very sensitive, and this causes some of these spikes. Another reason is, of course, that the power supply comes at 50 or 60 hertz, depending on whether you're in the US or Europe, so that also appears as a resonance in the detector. So these are various mechanical resonances in the detectors.
Thank you so much. Sorry to interrupt.
Yeah, no problem. Okay, so we're talking about neutron stars that are tidally interacting when they're close together, and mathematically we express it in the following form. If you have a initially spherical neutron star or any spherical object, frankly, and you put it in external tidal field, it will of course grow a quadruple moment. This is what every object does. The Earth does that, the Moon does that. When you have two neutron stars, you have this process going twice. So one object is causing a tidal field. In the equation I have here, this is depicted by the epsilon quantity, and that tidal field raises a quadruple moment on its companion. This is the Q quantity. And the constant of proportionality is the main quantity we'll be talking about with gravitational waves, called tidal deformability, and tells you how easy or how difficult it is to deform a neutron star. And that depends on the equation of state. The bigger the neutron star, the less compact it is, the more easy it is to deform it, the larger this parameter is. So a large tidal deformability basically tells you that the neutron star is big. It has a big radius. So the equation of state, the pressure is not very high. So the pressure is high. So, okay, in practice, what we actually measure with gravitational waves is not the combination of all various parameters of the masses and the tidal parameters given by the quantity at the top, but the plot on the bottom shows you more or less how exactly this affects the signal. So this is a gravitational wave signal from two neutron stars. of the same properties, the same mass, the same spins, but all they've changed is the tidal properties of the neutron stars quantified by this parameter lambda. At the top and the bottom shows you the time and the frequency domain, but let's focus on the bottom for now, which is the frequency domain. And if you follow with your eyes the peaks and the troughs of the signal, you will see that the blue is a little bit accelerated compared to the pink, and which is again a little bit accelerated compared to the green, which tells you that if you increase the tidal interactions, if the neutron stars are tidal interacting more, the signal proceeds faster, the evolution goes faster, which is what we were seeing in the simulations earlier. So this is basically the effect we're using to measure tidal interactions in those neutron stars that we observe with gravitational waves. So the first time this was applied was for GW170817, a detection of 2 neutron stars merging about 3 years ago now. And the plot on the right shows you the measurement of the tidal properties of the 2 neutron stars. So you have 2 neutron stars, so you have 2 tidal parameters describing their properties, lambda 1 and lambda 2. And the different colors, the different colored lines, the orange, green, and blue, show you measurements for tidal parameters under a slightly different analysis and slightly different assumptions. The details are not too important, but the general picture that seems to be coming out of 170817 is that the tidal properties were on the low side. So you see that the measurement is concentrated on the low end of the tidal parameters. So we can rule out less compact neutron stars and point to more compact neutron stars. We can rule out large radii of like 15 and 14 kilometers and point more towards slightly smaller radii for the neutron stars.
Hi, there was a question in chat. I want to ask quickly how superfluidity could modify these results.
So this is one of the things that always, details of the microscopic equation state always come up, and trying to understand what we can learn about neutron stars. The complicating factor here is that we measure bulk properties of the neutron star. So we measure the radius, or we measure the tidal parameters, which depend on the entire neutron star properties from the crust to the core. So if you modify something specific in the equation of state, it's not very clear how exactly this will manifest in the macroscopic properties that depend on the entire equation of state of all densities. And there are a lot of ways to mask properties left and right. So to answer this, we basically need to understand exactly how the radius will be modified, and if it can be modified in a way that is not degenerate with other effects. So this is one of the things that I think need to be a lot more discussed and understood in the future. How small microscopic shifts in the equation of state depend on the large bulk properties of the neutron stars. Does that answer the question, Andrew?
Yeah, please continue. Yeah.
Okay. So since then, we've had one more detection of a likely binary neutron star. The exciting thing about this was that it was much heavier than any other binary neutron star we've ever seen. So this is a plot of the masses of neutron star binaries we've seen in the galaxy, as well as GW170817. And this new event was much more massive, was about a 5 sigma outlier in the mass distribution. So this is both good and bad. It means that we have massive neutron stars out in the universe that form binaries and merge, so we can observe them. And because they're more massive, they probe higher densities in the equation state. The con is, of course, that the more massive a neutron star is, the more compact it is. So any tidal interaction in the system is intrinsically weaker. It's just harder to measure them intrinsically. So for example, for this event we're talking about here, we weren't able to obtain any interesting information about the tidal interactions because our upper limits, if you compare them to what we expected to see, are much higher than what we expected to see, so they don't put any new constraints. But the good news is that these systems are out there, they exist, they do merge. So with better detectors that we're currently in the process of making, we could extract information about the high density equation of state from these kind of systems that now we know do exist. Going forward, there's going to be a lot of opportunities and challenges for the next few years. A big challenge is going to be systematic uncertainties like any other measurement. We rely on waveform models for this sort of analysis, models that can track the phase evolution of our systems. And for current observations, we believe that the current models are okay. We don't see any evidence for waveform systematics. But going forward, at design sensitivity, which means in a few years, any measurement we would have would potentially be subject to waveform systematics. So we need better waveforms, and there's a lot of active development in the modeling community to try to meet the demands of improved detectors. But also there are a lot of opportunities going forward. With better detectors, we'll see a lot more systems. So if you put down the numbers, we expect something like to measure the neutron star radius to about 1 kilometer in the coming years with the more detections we expect to get. So this is one of the opportunities for the coming years. And of course, depending on what exactly we observe, because we don't know what exactly we'll be observing, but depending on exactly what we observe, there's also the opportunity to say something about quark matter inside the neutron stars. This will, of course, depend quite sensitively on what masses we're observing for the neutron stars. If they all have the same mass, we won't really be able to do anything in terms of measuring the shape of the exact shape of the equation of state, any features in it, like phase transitions. But if we probe neutron stars with very different masses, it is possible in the coming years to also find features like bends and kinks in the equation of state that could point to phase transitions. I would like to also briefly talk about the post-merger, because this is something that we expect to come in the next few years. We haven't seen it yet, but it will eventually happen. And roughly speaking, there are three possible outcomes for what happens when neutron stars merge. You can have a long-lived neutron star that emits a long duration signal that's harder to measure because the amplitude is lower, or your remnant could collapse directly into a black hole, and this would emit a signal that we cannot observe, unfortunately, because the frequency would be too high. But there's this scenario where the remnant could survive a little bit as a neutron star before collapsing into a black hole. This is the middle scenario in the picture here. And that would be the most promising case for us, because then you have a signal in around 2,000 to 4,000 hertz in gravitational waves that we can measure with slightly improved detectors that are coming in the next few years. So this is a plot of what the signal looks like in this case. This is a time frequency plot in the center, and the top and the right is the signal projected in the time domain or in the frequency domain. But if you focus on the one in the right, in the frequency domain, you'll see that most of the emission comes in one characteristic frequency that is related to the F modes of the remnant star. And that depends quite sensitively on the equation of state. So if I pull back the simulations from earlier of the merging neutron stars, and you see the merger phase where they have a single remnant formed by the two cores that have collided together, you'll see that the one on the left is kind of smaller. It's also rotating a little bit faster than the one on the right, which is less compact and is going around slower. So exactly the compactness of the remnant star, its density, all affects the frequency at which the post-merger signal comes. So if we can measure it.
Just a couple minutes left.
Okay, thank you. So if we can measure it, we can say something about the equation of state. Unfortunately, this did not happen for 170817. We did not have the sensitivity, so we have not seen this signal yet. But with improved detectors in the coming years, this is possible to do it. So this is actually an animation. I'm going to start playing it. And what it basically shows you, it's the blue is a fake signal, a simulated signal we've put in our data. And we gradually improve the detector. So the detector improvement is shown by the dashed line. So the dashed line goes down, and the more down the line goes, the more improved the detectors are, the lower the noise in the detectors. So the signal is coming out of the noise, and the analysis can pick it up. The analysis is a shaded region. So we expect in something like 3 times the design sensitivity of our detectors to be able to see such a signal. And I realize that 3 times the design sensitivity sounds scary, but this is within reach of either proposed or funded instruments. So we expect the instruments around 2025 to already be better, about 2 times better than their design sensitivity. So it is possible to see such a signal around 2025, maybe a little bit further out. And the big opportunity coming from these types of signals is that they offer complementary information to what we see before the merger, because when the neutron stars merge, whatever they form has a higher density than before. So we can probe higher densities and higher temperatures in the equation of state. So you have a better chance of seeing things like phase transitions that happened at higher densities, perhaps, than what you could achieve with normal neutron stars before they merge. Okay, and finally, with the last few minutes remaining, I wanted to briefly touch upon neutron star black hole systems, because there are some tantalizing detections lately about possible neutron star black hole coalescences, and you might hear a lot about those and what they say about the equation of state. So roughly speaking, when you have a neutron star and a black hole colliding, you have 2 possible outcomes depicted by the 2 signals here, the blue and the red. In the blue case, you basically have the neutron star just falls into the black hole. You don't have much time for any tidal interactions or anything like that. So the neutron star simply falls into the black hole, and you get something like the blue signal. On the opposite extreme, the neutron star could be completely torn apart during this process. And you have something like the red. You no longer have a neutron star orbiting around a black hole. The neutron star is completely torn apart, and the signal just shuts off. So where exactly this happens and what exactly we're going to see depends on the properties of the system, but whether we see the red or the blue type of signal could be used to say something about the neutron star equation of state and whether the neutron star was deformed before the merger.
We need a couple minutes for questions. Are you close?
Yeah, this is my last slide. I just wanted to point out there's a detection of a possible neutron star black hole system. We're not sure exactly what it is because the low mass object is 2.6 solar masses. So it could be either a black hole or a neutron star. But there's a lot of ongoing discussion in the literature involving a lot of you about what exactly this object is. And unfortunately, gravitational waves cannot tell us the answer because a 2.6 solar mass object looks the same whether it's a neutron star or a black hole, because tidal interactions in very large objects are hard to measure. So we need a lot of guidance also from the modeling community about what these sort of objects could possibly be. I will just then conclude that our next step is the 4th observing round, where we expect a lot more detections. The timescale has actually been pushed a little bit back. We expect this to start not before mid-2022, but the detectors are improving, and we